The biggest shift here is that AI is moving from reasoning over text to building and auditing structured knowledge and ideas. One system is learning to generate scientific hypotheses in a traceable graph. Another is turning the entire scientific literature into a navigable reasoning map. And the third is showing where graph language models are still faking structure instead of truly understanding it. That matters because the next wave of research tools won't just answer questions, they'll explain how they connected the dots. Here's what that means for scientific discovery, retrieval, and graph-native AI. Let's explore the first paper. Graph-native reinforcement learning enables traceable scientific hypothesis generation through conceptual recombination. Graph Preflexor is a graph-native reinforcement learning framework for scientific hypothesis generation that turns the hidden reasoning trace into an explicit sequence of is less than brainstorm, is greater than, is less than graph, is greater than, is less than graph. JSON is greater than, is less than, patterns is greater than, and is less than synthesis is greater than stages. Then optimizes that structure with ARPO cold start and group relative policy optimization, GRPO, built on Quinn 3, 1, 7, B, Llama 3, 2, 3B, Instruct, and Quinn 3, 8B, Backbones. The system is evaluated on 100 open-ended materials, science, and mechanics questions judged by Claude Opus. 4, 7 on 0-10 scores, where it improves aggregate reasoning performance by 40-65% over the corresponding base models, with the largest gains in traceability. Embedding analysis with Google, embedding Gemma, 300M, and BAAI, BGE, Base, N, V1, 5 shows roughly 3 times greater semantic diversity, including interphase cosine distance gains from 0.07 to 0.2 at 1, 7B, and from 0.08 to 0.21 at 8B. Semantic backtracking shows graph, pref, lexor, 8B final answers align with its own structured reasoning in 92 of 100 cases, and specifically with is less than synthesis is greater than in 89 of 100 cases, while Quen 3, 8B, aligns with its own thinking trace in only 16 of 100 cases. Test time graph expansion over 2,000 iterations on self-healing biopolymer composites shows that Explored's semantic volume saturates within a few hundred iterations, but surprising recombinations continue to grow superlinearly, culminating in a leap graph with 4,419 nodes and 37,064 edges, and revealing that additional compute mainly densifies a bounded idea space rather than expanding it indefinitely. Let's explore the second paper, SciAtlas, a large-scale knowledge graph for automated scientific research. SciAtlas is a large-scale, multidisciplinary knowledge graph for automated scientific research that targets the failure modes of keyword search, vector retrieval, and LLM deep research workflows, especially their weak topological reasoning and hallucination risk. Built from OpenAlex and deployed in Neo4j, it organizes 43 30M papers across 26 disciplines into 157M entities and 3 B triplets with 9 node types, 12 relation types, and 1024 dimensional embeddings over titles, abstracts, and keywords. A lightweight Quen 330B, A3B Instruct 2507 extractor generates 3 8 canonical keywords per paper, while BGE, large, N, V1, 5, and BGE, re-ranker large, support hybrid semantic retrieval. The core retrieval pipeline uses tri-path collaborative recall keyword matching, semantic matching, and title matching followed by 2-hop graph propagation with random walk with restart, citation-aware weighting, and graph re-ranking. It returns the top 2 zero papers with path-based explanations in under 2 minutes. The paper's novelty is not a benchmark jump, but a deterministic, neurosymbolic, cognitive map for literature review, idea grounding, trend synthesis, author retrieval, and researcher profiling designed to reduce inference cost while preserving deep association discovery. Let's explore the third paper, When Graph Tokens Sync, a mechanistic analysis of graph language models. This paper from UVA and Capital One performs a mechanistic audit of graph language models, focusing on LAGA and TEA GLM built on Vicuna 7B llama family backbones. The authors show that so-called graph sync tokens are sparse activation outliers across Quora, ArcSiv, and PubMed. A small set of hidden dimensions repeatedly spikes, especially dimension 1512, while LLaga also inherits the known llama2 sync dimension 2533. However, this saliency does not make them the main carriers of graph information. In TEA-GLM, the strongest sync positions are mostly indices 0 and 1, yet query-to-graph attention often concentrates on later slots, and logit lens decoding usually returns weak, generic domain terms such as paper rather than labels or topology-aware concepts. Direct interventions reinforce the same conclusion. Pruning the top two sync tokens barely changes node classification or linked prediction, while removing random non-sync tokens can be more harmful, and moving sync tokens to the front in LLaga produces only minor shifts. The key result is a decoupling between activation level saliency and graph semantic utility, suggesting that current graph token construction and alignment methods do not reliably produce topology-aware internal representations inside the LLM. That's a wrap on today's AI paper highlights. Thanks for watching.